Hey everyone, so we're going to talk about the next part of Newton's three laws, which is Newton's second law. This pretty much talks about how objects move. So first law talks about whether or not an object would move, why it moves, and if it moves or changes its motion. I should clarify that when I say moves, I mean changes motion. But Newton's second law tells us how it actually ends up moving, and it gives us a relationship between the forces that we apply to an object and the acceleration that the object experiences. Remember, we talked about in the first one that objects that have unbalanced forces will end up accelerating. So this law is kind of focusing on that specific aspect. Uh, Basically, the entire law is just this equation: F net equals ma. So that's all the second law is. It's just F net equals ma, which you call it the law of FMA, but whatever. The basic idea is that there's a linear relationship between the amount of force that you apply and the acceleration that it experiences, and that the mass of the object is inversely related to the acceleration. So this means that objects that are heavier will experience less acceleration when you apply the same force to it. Likewise, if you have an object of equal masses and you apply twice as much force on one object, you get twice the acceleration. That's basically what this equation says. Now, this equation is critical for this class, for not only this topic, but this class in general. Like I said, a lot of equations that we're going to talk about in later topics will actually have roots based from this F net equals ma equation. So this is a very important equation. And like I said, we end up using it so much. In fact, one of the things that I'm going to end up talking about later on is the steps that you have to go through when doing a problem. And typically, the very first step in doing a problem will be to draw an FBD. The next one is to do your F net equals ma equation. And that's one of the things I'm going to say is, do your FBD, do your sum of the forces, because those two parts are critical and important to setting up problems. I should point out that a lot of times you might actually see me rewriting this in a slightly different way as sum of the forces equals ma. Remember that the net force is just adding up the forces in a certain direction. So you could talk about sum of the forces in the x direction is equal to ma, or sum of the forces in the y direction equals it to ma. I kind of flip flop between using the two terms. I like F net equals ma more, but I think writing it like this, sum of the forces equals ma, helps remind people that we can find the net force by looking at our FBD, looking at the forces in a certain direction, and then adding them up, right? So one thing I do want to point out, and I don't know why I have to talk about this. It's a very silly thing to talk about, but it's something that the AP wants me to talk about. It's the difference between what's called inertial mass and gravitational mass. That there's technically a difference between these two terms. Uh, so inertial mass is any mass that is found using F net equals ma as the basis of that. So the idea being that if you do an experiment where you apply a force and then you measure measure the acceleration from it, you can get the mass of the object. And when you do that, you get the inertial mass. And in the variety of different equations that we have that is based off of F net equals ma, we'll end up producing the same result of finding the inertial mass. Well, what about gravitational mass? Gravitational mass uses a variation on F net equals ma, which is the second equation, which is also extremely important, which is Fg equals mg. Now, Fg equals mg tells us the weight of an object on the surface of the Earth. Now, where does this equation come from? I think it's important to note that this equation doesn't come out of nowhere. F net equals ma came from experimentation, looking at the forces acting on an object, applying a force, measuring its acceleration, and seeing the relationship and how mass plays into it. Fg equals mg comes from the fact that if you have an object that is in free fall, the only force acting on it is force of gravity. So if we look at the F net equals ma equation like this force of gravity is our net force. And the acceleration it experiences is what we call the acceleration of gravity g. So that's where the Fg equals mg comes from. But it's one of those equations that, again, we use so often. A lot of times you're going to have an object, they're going to tell you the mass, and then you just do F equals mg real quick to find out what the force of gravity is so that we can then, set up our FBDs and find that net force. So I just want to point this out that F equals mg is a very specific version of F net equals ma. All right. But the idea here, going back to what I was talking about, the difference between inertial mass and gravitational mass, is that if I use F equals mg as a basis of finding the mass, that uh, it is then gravitational mass that we're finding. Common examples of this would be things like hanging an object from a spring scale. The spring scale measures the FG of the object and uses that to find the mass. So that would be using Fg equals mg. Pretty much anything that requires gravity. That's what I usually say is that there's no difference between the two values. I just want to point that out that uh, there's only one question that they ask, and it's literally which of these experiments would find inertial mass or which of these experiments would find gravitational mass. And the way I always put it, the easiest way to think about it is that inertial mass can be done in space. Gravitational mass cannot be done in space. So any experiment that requires gravity in order to work would end up finding the gravitational mass. Perfect example, placing an object on a triple beam balance. That requires gravity. No gravity, it would not pull it down. That measures gravitational mass. Putting an object on a spring and having it oscillate around, that does not require gravity. That can be done in space. That would be inertial mass. So there's a variety of different experiments, and I think I'm going to show it every now and then. I'll pop this up, say like, oh, here's an example. This can be done in space. This would be inertial mass. But like I said, it's a one-off question. I wouldn't put too much stock into it. I just want to make sure I mention it at least once so that if you ever see the phrase inertial or gravitational mass, you're not thrown for a loop. All right. So yeah, here's the first two questions. Pause the video, works off. I'll go over in a second. All right, so we're just doing some practice with the F net equals ma equation. Now, I do want to point out, I kept mentioning that a lot of times I want you to start off drawing FBDs. It is important to note that you really only need the FBD once you start talking about two or more forces acting on an object. A question like this doesn't really need it. It's pretty basic. It's bare bones. So we just use the equation. First one, they give us the mass, they give us the acceleration, they want the net force. So F net equals ma, 100 times 23 we get 2,300 newtons. Question 8, they want the weight of the object. The weight is Fg, so we're going to use Fg equals mg. Uh, take the 100 or times it by 10, which is what g is, and we get 1,000 newtons. It's important to make sure that you differentiate these equations. Technically, they are nearly identical in structure, as in it's force equals mass times an acceleration. So if you do accidentally use Fg equals mg up here, like if you said this is Fg equals mg, but then just plugged in 23 for g, obviously you would get the same equation, the same answer because it's still mass times acceleration. However, you do want to get into the habit of not doing this. Make sure that you're doing F net equals ma when you're talking about net forces and the acceleration the object is going through. You're using Fg equals mg, Fg equals mg when you're finding the weight of the object, and not necessarily using the accelerations it's moving. The important thing is that when you're using this equation, this a represents the acceleration the object is actually experiencing, like it's moving and changing its velocity based off of that acceleration. The g in here is actually just what the object experiences being on the planet. So uh, regardless of how the object's moving, it will always feel mg, Fg equals mg, because gravity is always pulling down with this 10 meters per second squared on the object. It's just that we're not moving because the floor is, keeping us from moving further down. So try not to overthink it. Just keep in mind that Fg equals mg is something that always acts on us because we're on the Earth, um, and we don't have to be moving in order to find it or calculate it. But F net equals ma, we have to have that acceleration to use this equation. All right, here's the next two. Pause the video, works off. I'm going to go over a second. All right. So again, question 9, we're using the F net equals ma equation. Take the numbers, plug them in, and we get our answer. Easy enough, 20. Okay, now Question 10. Here we're starting to see what's going on when we have these two forces. So we have a 50 newton force to the right and a 28 newton force to the left. Now this is again basic enough where you probably don't need an FBD, but humor me. We have 50 going to the right. We have 28 going to the left. According to my F net equals ma equation, the net force has to be the difference of these two forces because they're going in opposite directions. So I'm going to have to do 22 newtons for F net because 50 minus 28 is 22. Plug in the mass like we just got, and we get 1.1 meters per second squared as the acceleration. All right, here's the next one. Pause video, work itself. I'm going to go in a second. All right, so they want us to basically figure out what force represents the or which diagram represents the force acting on the block by the table. This you're going to have to pay attention to the wording. Now, this question is basic enough. Again, the structure and the choices, but you have to be able to note the difference between something like the force exerted on the block by the table, which is slightly different from the force exerted on the table by the block. Right? Switching the term block and table changes something, and we're gonna see that later on in this unit when we talk about what's called multi-mass systems. We're going to talk about the difference in the way that it's phrased, but for the most part, the key thing is that we're looking for the force, and in this case, because it's the force on the block by the table, this is just another way of saying which one of these represents the normal force, right? Because that's the contact force, the force between these two objects that are in contact. So we're looking for a normal force. Now, for the most part, I can get rid of choices 2 and 3 because they're both in kilograms. These are not forces. So only choice 1 and 4 are measured in newtons. If we look at the 500 kilogram, so not 500, 5 kilogram object, it is experiencing two forces. It's experiencing a force of gravity going down, and according to Fg equals mg, it's going to be 5 times 10, which is 50. Now from here on out, I'm going to immediately just tack on a 0 when I find Fg. This is one of the reasons why I like using 10 for G, because it makes it so that once I see 5 kilograms, I can say, okay, that's 50 newtons. I don't have to worry about anything crazy like that. So it experiences a 50 newton force pulling down caused by gravity. And then there's a normal force from the table pushing up. And because of the fact that the object is at rest, uh, this object this object is in equilibrium, which means that these two forces have to be balanced. So if there's a 50 newton force going down, there must be a 50 newton force going up. So this one is not the force normal, which should be pushing up. This one's the force normal. All right. Here's the next one. Pause the video, works up. I'm going to go in a second. Now, here's a question that is pretty much the bane of the existence of a lot of physics people. You have to be super careful with the way this is worded. It says the man on Earth has a mass of 98 kilograms, travels to the moon where we have a different acceleration to gravity. They want to know the mass on the moon. The answer is 98 kilograms, because the key thing is that mass never changes. The mass of an object never changes. It doesn't matter whether you're on the Earth, on the moon, on Jupiter, in the sun, or in a black hole, your mass is the same mass regardless, because mass is the amount of matter and material you are made up of. So unless you're cutting off a limb, you are not losing any mass, or your mass isn't changing. Um, the big thing that people do is they tend to mistake this for force of gravity, and they do all that stuff. So again, you gotta look deeper into this question and pay attention to the way it's worded and what they're actually asking for. All right, the force of gravity changes. Fg will change. That's why we have an equation for it. It depends on how much gravity is on the planet. On a planet like the moon, not a planet, sorry, the moon, or a place like the moon, there is a lower gravitational acceleration there. Therefore, we would experience a lower weight, but our mass stays the same. And that's pretty much it when it comes to the second law. We're going to be using this equation a lot more throughout this entire unit. Like I said, it is critical for just not only this topic, but future topics as well. If you have any questions, feel free to let me know. Otherwise, good luck and have a great day.